Before we start talking about our project, first let us understand how the Qt Creator works. This is the welcome screen of Qt. If we want to create a new project, click on the New Project button and then choose the non-Qt project template if we want to build a normal application either in C or C++. I have written my code in C++, so I will choose the non-Qt project template and then choose plain C++ application. Here I can title my project. Suppose I title it as example 1. Here we get to choose the build system for our project. Qt by default provides the QMake build system and I will use the QMake build system. Now click on next. You can select the kits that you want for your project over here. After doing so, click on next and then finally click on finish. We can see that the project is created here. The main.cpp is a space where you can write your code in either C or C++, and .pro file is the space where you have to include all the libraries and the library paths that are essential for your project. I have written a normal code that reads an image and displays it. The functions imRead, imShow are all available by OpenCV. The .pro file over here contains all the libraries and the library paths that are essential for our project. Once you have written your code, you can build your project using the hammer icon that is available on the bottom left corner of the screen. The green color bar on the bottom right corner of the screen shows the build status. Here we can see that the project is successfully built. Once your project is built and there are no errors, you can move forward with running your project using the run icon that is available above the build icon. The output is shown. This is how the normal application works in Qt. Now let us get back to talking about our project. The project that we built was implementing the perspective transformation using OpenCV on embedded GPU. We have all been using document scanners like CamScanner since a long time. What we basically do while using CamScanner is that we crop the required portion of the image and the application scans it and provides the output image. The application that we built serves the same purpose in a way. It provides the top-down view of an image, that is, it eliminates the unwanted portion of the image. An important feature of our application is that it automatically detects the document and provides its top-down view. This is the fact that differentiates our applications with the document scanners like CamScanner. Getting the top-down view of an image and removing the unwanted portion is also known as getting the perspective transformation of an image. After obtaining the perspective transform of an image, we can apply the thresholding operation to get the scanned image. But how do we get the perspective transform of the image? The algorithm for the same has been divided into 3 parts. First, edge detection, second, finding the largest contour, and finally, applying the 4-point transform. If we want to open an already existing project in Qt, you will click on the Open Project button on the welcome screen. You will select the project that you want to open and then open its .pro file. Thus the project opens in Qt. Now we can here see the code available for our perspective transform operation. Let us understand how this works. This is the main function of our code. After reading the image, we have used the resize function available by OpenCV to resize the image. This function is capable of resizing the image to any specified size. After resizing the image, we have called the preprocess function. What does the preprocess function do? Let us see. As the name suggests, the preprocess function does preprocess the image before it moves on to contour detection. The CVT color function is used for converting the image into grayscale. Then we have created a structuring element for the morphological opening and closing operations. The process of opening an image will smoothen the edges, break narrow block connectors, and remove small protrusions from a reference image, whereas closing an image will also smoothen the edges, but it will fuse narrow blocks and fill in small regions. Thus, to summarize, opening and closing when used simultaneously provide better edge detection. After opening and closing, we have used the Gaussian blur function to remove all the high frequency components from the image and blur the image. Next, we have used the Kenny edge detector. So why have we used the Kenny edge detector and not Sobel? Sobel, even though being simpler than Kenny, suffers poorly under noisy conditions, whereas Kenny has an inbuilt structure that provides better and accurate results even in noisy conditions. Here, the process of edge detection is complete. Now, let us move on to finding the contours of an image. Contour is always a vector of points, and hence we have defined it as vector of points. Then we have used the function find contours, also available by OpenCV, to find the contours in an image. Here we have made an approximation. There is an assumption that we have made henceforth. The largest contour with 4 points on it is our required document. This is a fairly safe assumption. Why? Because we want a top-down view of a document. Document is a piece of paper, a rectangle with 4 edges, and hence it is a safe assumption that the largest contour with 4 points on it will be the contour of our required document. So to find the largest contour, we loop over the contours and find the largest ones, discarding the rest of them. The function approx_polydp approximates the contours with given specifications. Now we loop over the largest contours to find the one with 4 points on it. When we have found the contour with 4 points on it, the contour thus found will be the contour of our document. Next, we have used the draw contours function, also available by OpenCV, to draw the contour of our document. The draw contours function in general can be used to draw the contours in an image. Now we move to the final step of our application, that is finding the 4-point transform. But first, let us start with finding the ordered points. To find the ordered points, we pass the points on the detected largest contour and then sort all those points on the basis of their x coordinates. On doing so, we get the leftmost and the rightmost points. Now, sorting the leftmost points on the basis of the y coordinates provides us with top left and bottom left points. Now, considering the top left point as an anchor, we find its Euclidean distance with the remaining 2 points. The Euclidean distance between the top left point and the bottom right point will be the maximum because it will form the hypotenuse of the right-angled triangle. The distance between the top left and the top right point will be minimum of the two. Thus we get all the 4 points. Now we pass all of these points in a specific order. The order of these points is very crucial to be maintained throughout the code. The order that we have maintained here is top left, top right, bottom left. Once we have got the ordered points, it is easy to find the width and height of the document. Then we create a vector which contains the old configuration of the document in the image. We create another vector which will contain the new configuration of the document. The new configuration has its top left points on the 0, 0, and all the other points are mapped accordingly. The getPerspectiveTransform function, on passing these two vectors in the getPerspectiveTransform function, we get a matrix that contains the new configuration of the points. On passing this matrix into the warp perspective function, we get our warped image, that is the perspective transformed image. After getting the perspective transformation of the image, we can apply the thresholding operation and then blur the image to get the scanned version of the warped image. Here is the output of our code. This is the original image, this is the warped image, and this is the scanned version of the warped image. As the final task, we built a GUI using Qt and OpenCV libraries. The GUI consisted of a set of push buttons and a label that was used to display the output image. Let us talk about Qt. Qt is a cross-platform application framework. We used it to develop a graphical user interface for this particular application, owing to its well-designed API binding to any language, namely C++, Python, C#, Ruby, and rich set of widgets. Widgets like push buttons, labels, editors are all building blocks of the GUI. Let us go through some of the Qt tools. Qt Linguist. Excellent support for translating Qt C++ and Qt Quick applications into local languages. Qt QMake. QMake is a utility that automates the generation of makefiles. Makefiles are used by the program to build executable programs from source code. It contains a set of directives. Qt Core. It is responsible for file input-output, event and object handling, and multi-threading operations. Qt GUI. It is a set of customizable widgets, 2D graphics canvas, and OpenGL integration, powerful font and layout engine. Qt Designer. It is a GUI layout and forms builder. Now, how to design a GUI using Qt. Let us have a brief overview. Click on the new project, and this time we will select the application template. In the application template, we will select the Qt widgets application. We will title our application, for example, example 1. Then we will select the kit that we want for our project and then click on next. Here the class name and the header file name should be the same, and it will always be the same. For example, if I change this name to example, the header file name also changes to example. Thus, both of these files always have the same name. Click on next and then click on finish. This is the Qt GUI project opened. There are various files over here. There is a .pro file again that includes all the libraries and the library paths essential for our project. We have a .h file that is the header file. This file will contain all the functions that will be used in the main window.cpp file. The main window.cpp file is a space where we will have all the backend coding of the widgets that are used in the .ui window. Now let us understand how the .ui window works. As visible, the .ui window has many widgets, for example, horizontal spacer, vertical spacer, push button, tool button, radio button, checkbox, etc. We will see the working of a push button. Suppose I want to make a GUI that closes on pressing this push button, and hence I will change the text in this push button to close. We can also change the object name of this push button by modifying it over here. It establishes a communication link between the task to be performed on pressing the push button and the activity performed on the push button. So we will click on the Edit Signals and Slots button over here and then click on the push button. Now drag the cursor anywhere on the window. A dialog box will pop up. Select this checkbox at the bottom and then select the signal that you want on your push button. I want the action to happen when my push button is clicked, so I will double click on clicked, and then we can select the action that we want to happen on clicking this push button. Here I will choose the close slot. Here I will choose the option close and now click on OK. Build this project, and on running it we see a push button that is available on this window. On clicking this push button, the main window will be closed. This is how the Qt GUI works. This is the .ui window of the GUI that we created. And this is the .cpp file which contains all the backend coding of the widgets used in the .ui window. As we can see, we have used the various push buttons that name different image processing operations on the image. And this is the label where the output of all these operations is displayed. Let us run this. This is the GUI that we created. The Open Image push button enables us to select the image that we want to scan. Here I want to scan the image ticket.jpg. We can see the chosen image in this label. On clicking on the scan push button, the scanned version is obtained. We can get the original image, that is the warped image, using the original push button. On clicking on the grayscale button, we get this grayscale version of the warped image. We get the edges of the warped image on clicking on the edges push button. We get the black and white version of the warped image on clicking upon black and white. Black and white 2 is a little bit different from black and white. It shows darker components, and the black and white push button shows the whiter components. The rotate clockwise push button rotates the warped image in the clockwise direction, and rotate anti-clockwise button rotates the image in anti-clockwise direction. This was all about the GUI that we built.